Okay, so starting from the beginning again, the fungus yeast contains the enzyme catalase. So even if we haven't heard of this enzyme catalase, we can make some assumptions about this enzyme. We know that all enzymes are biological catalysts that speed up reactions, and as they speed up reactions, they themselves are not used up within the reaction. We know that enzymes are made from the monomers amino acids, that they're globular proteins with a specific 3D shape that's determined by their tertiary structure. And we know that enzymes are affected by certain conditions such as temperature, pH, concentration of substrate, inhibitors, and cofactors. Now we're told that this enzyme catalase speeds up the decomposition of hydrogen peroxide. Now we know in this instance we're not talking about decay by microorganisms. It just means that the hydrogen peroxide is being broken down into its components. And we have this reaction outlined for us here. So hydrogen peroxide is converted into water and oxygen gas. Now if we want to measure the rate of any chemical reaction, we can do that by measuring one of two things. We can either measure the disappearance of the reactants that are involved or the appearance of products. So in this case we can measure the rate of the hydrogen peroxide being used up, or we can measure the rate at which water or oxygen appear as products. Now for any reaction, always look to see if there is a gas involved, because gases are always much easier to collect. They're much easier to measure the rate of production of. So in this case I would assume that oxygen as a product there is much easier to measure the rate of appearance of rather than the water. So just as always, for any enzyme catalyzed reaction, we just get clear into our heads what the reaction is. So we've got hydrogen peroxide here, which is the substrate for this enzyme catalase. So catalase as an enzyme is converting this substrate, hydrogen peroxide, into water and oxygen, which are the products. We have a balanced equation here. We know that there are 2 moles of hydrogen peroxide being converted into 2 moles of water and 1 of oxygen. Okay, so a student decided to investigate the activity of catalase using the apparatus shown in figure 1. And the total volume of gas collected was recorded every 20 seconds. Now, from the equation that we're given here, we know that the gas that must be being collected is oxygen. So every 20 seconds they're recording the volume of oxygen that's being produced. So this is the setup that the students use. We've got a test tube fixed in a clamp stand with a tube leading to an inverted measuring cylinder. Now inside of the test tube it tells us that we've got 10 cubic centimetres of 5% hydrogen peroxide mixed with 5 cubic centimetres of yeast solution. Now from what we were already told in the question, the fungus yeast contains the enzyme catalase. We know that this yeast is present because it's the source of the enzyme, it's the source of the catalase enzyme. Now, as this reaction occurs, the oxygen being produced will start to progress up the tube, through this tube here, and eventually up into this inverted this cylinder. And the gas will accumulate up at the top here. So this space here is representing the gas that's accumulated. We have a scale on the side of a measuring cylinder, so that can be used to measure the volume that's present. And these bubbles obviously must be the bubbles of oxygen as they're being created in this reaction here. Okay, so the independent variable in this reaction, if you remember I choose the values of, I would choose to record every 20 seconds. So the independent variable here is time. And every 20 seconds I'm recording the volume of gas, the volume of oxygen that's being produced. So the dependent variable is the volume of oxygen. So time here is recorded in seconds, and the convention is to record that as a lowercase s for the unit there. And the volume of oxygen is cubic centimetres, and I've just took that from the y-axis here. They've actually told us the units in the question. So looking at the results that this student's gained, they've plotted the results time on the x-axis over volume of gas, which is on the y-axis here. So if you always remember that the independent variable should be on the x-axis, and the dependent variable should always feature on the y-axis. So here, what the students done is they've plotted their results, and the plotted results are shown by this solid black line, but they've extrapolated a line here. So from 0, where that initial reaction begins, they've then used this dotted line to extrapolate. And now what they're showing here is what would happen to the volume of oxygen if the reaction was to progress at the same rate that it does at the very beginning of the reaction. So this is called the initial rate of reaction. And the initial rate of reaction, if you think about it, is always much, much faster, because this is where you have the maximum concentration of reactants. So at the very, very beginning of the reaction here, we're going to have the maximum number of hydrogen peroxide molecules, the most that we'll ever have, because as time progresses, these H2O2, these hydrogen peroxide molecules, are going to start getting broken down by the enzyme catalase. So here, this is where we've got the maximum number of substrate molecules, therefore the maximum number of successful collisions and the maximum amount of product that's going to be made. So this dotted line is just representing what would happen if we always had that maximum number. What would the rate and what would the volume of gas look like if we were to continue to progress at that very, very initial rate at the beginning? But like I say, we know that the substrate molecules over time will get converted into a product by the enzyme catalase. So this is why the reaction looks like it's starting to level off, and the volume of oxygen doesn't get any higher once you reach a certain point. Okay, so this is because the reactants, the substrate molecules, the hydrogen peroxide, is starting to run out. So we're going to have fewer enzyme substrate collisions, therefore we'll have fewer enzyme substrate complexes, and therefore less product in this case, which is the the oxygen gas that we're collecting. Now there comes a certain point, so it's around about from 100 to 120 seconds, where we see this plateau. So it doesn't matter how much time progresses from here, the volume of oxygen that we collect never gets any higher. Okay, so this is where we've reached our completion point. So all the H2O2, all of the hydrogen peroxide, has been converted now into water and oxygen. So this is the maximum volume of oxygen that can be made from the initial substrate that was added into the tube. And we know from the information that they've given us here, it was 10 cubic centimetres of 5% hydrogen peroxide. So this here must be the maximum volume of oxygen that we can make from that 10 cubic centimetres of 5% hydrogen peroxide. So thinking about it then, in any experiment we would always repeat our experiment in order to make our results more reliable. If your results are not reproducible, well then they're not valid. So repeat to make our results reliable. Now if we were to repeat this experiment, there are certain variables that need to be controlled. So think about temperature. If we increase the temperature, well then we would increase the rate of reaction, because molecules would gain kinetic energy, they'd move faster, collide more frequently, therefore make more enzyme substrate complexes, and the rate would go up. Likewise, if we were to decrease the temperature, well then the kinetic energy would decrease and the rate would decrease. So if you did your experiment, say at 10 degrees, but then repeated it at 40, your second experiment would look faster than your first, and you actually couldn't make a valid comparison between those two replicates. So likewise, if we were to increase the volume of hydrogen peroxide or the concentration of hydrogen peroxide, you would increase the rate of reaction, because with either of those scenarios you would have more molecules, you would increase the number of collisions, increase the number of enzyme substrate complexes, and likewise increase the rate. Similarly, if you were to decrease these factors, you would decrease the rate because there would be fewer molecules and fewer collisions. And lastly, the volume of yeast, because this is the source of our catalyzed enzyme. So if we were to increase the volume of yeast, you would in effect be increasing the concentration of enzymes present. And if you increase the concentration of enzymes present, you would increase the rate because there's an increased chance of successful collisions, it goes on. So this is all of the information that we can take from this very, very simple description of a very simple reaction with what is a very, very simple apparatus.